peek at if you want to. All right, so let's start off with this problem. Sample problem 4.15. I would say this is a totally reasonable problem for the midterm. This is a totally reasonable problem for your final exam. It says here that you have 0.10 molar HCl solution and you use it to simulate the acid concentration of the stomach. How many liters of stomach acid would react with a tablet, so like an antacid tablet, for example, containing 0.10 grams of magnesium hydroxide? So what we're doing here is a neutralization reaction, right? We're combining an acid, hydrochloric acid, with a base. Magnesium hydroxide is a base. Here's the structure of magnesium hydroxide, or the formula, I should say. And so what's the first thing we're going to have to do here is we're going to have to write a balanced equation. So why don't we start with that, and then we'll worry about numbers after, okay? So let's get cooking here and see if we can come up with a nice balanced equation. Now, we're really going to need our nomenclature skills here. We have magnesium hydroxide and we have hydrochloric acid. How are they going to combine? All right, we're going to do a double displacement in that, or a metathesis reaction, in that magnesium is going to combine with the chloride, and then the hydroxide is going to combine with a proton to make water. So again, we're taking a base, right? We take a base plus an acid, and we're going to end up with a salt, which in this case will be magnesium chloride. Now, what's the formula of magnesium chloride? Well, if I look at my periodic table, magnesium is in group 2A. It always has a charge of 2+, right? So we're going to have magnesium. And what's the charge of chloride? Well, chlorine is a halogen. Halogens gain 1 electron, right, when they adopt a charge. And so if we have 2+ and -1, we're going to have MgCl2. I've gone ahead and looked up in the solubility table that that is soluble. And then I'm also going to form water. Okay, so I form a salt in water. So remember, the magnesium chloride, that's a salt, right? Because it's the combination of a metal and a non-metal. Okay, and then we form water, of course. Now, water, remember, is a liquid. Water is not aqueous. Okay, so we always write water as a liquid. And you're like, well, what's the difference? Well, remember, an aqueous salt is going to be a strong electrolyte, whereas water is not an electrolyte. So it is important. All right, so we've got that. Is this equation balanced? I already think no, it's not. All we have to do is put a 2 in front of here, and now we have a balanced equation. Well, let's talk about what we're starting out with. And in the problem, I'm going to erase this spinach here quickly. In our problem, they tell us that we're starting out with this antacid. I call it an antacid because a base is usually an antacid. So we take 0.10 grams of magnesium hydroxide, and it's saying how many liters of 0.10 molar HCl could you neutralize with that? Now remember, going back to last class, remember how I said you can't compare grams and grams and molar, right? You have to compare what to what? You have to compare the number of moles of magnesium hydroxide to the number of moles of HCl. So we have to use our balanced equation to get a molar relationship. Now, you might be asking yourself, okay, well, here I have the number of grams of magnesium hydroxide. This is not a trick question. Mr. Dion hates trick questions. Could somebody just guide me in the right direction? How would I go to convert this mass in grams into the number of moles of magnesium hydroxide? Not a loaded question. Just give me the simplest answer. Aaron, Sierra, exactly. They just said, Matthew just said, go with molar mass, Mr. Dion. Okay, perfect. I like the way you think. So we're going to start out, and we're going to say 0.10 grams of magnesium hydroxide. We're going to use that molar mass, just like my students told me. They said, Mr. Dion, in 1 mole of magnesium hydroxide, you have a molar mass. Now, I've gone ahead and calculated this already. You add up the mass of 1 magnesium, 2 oxygens, and 2 hydrogens, and you end up with 58.33 grams of magnesium hydroxide. Now, this is all well and good. Okay, there's nothing wrong with this. In fact, it's perfectly right. But if I was to stop here, all I would have is the number of moles of magnesium hydroxide. I want to figure out how many moles of HCl, or stomach acid, could I neutralize. Could anybody tell me where I should go next to find my next conversion factor? Exactly. Thank you, Sarah. Thank you. Perfect. Exactly. All my students are on the right page. They're saying, go back to your balanced equation, Mr. Dion. Absolutely. So let's do that. I know that if I have 1 mole of magnesium hydroxide, I'm going to neutralize 2 moles of hydrochloric acid. So let's throw that in here. For every 1 mole of magnesium hydroxide that I neutralize, or that I use, excuse me, I'm going to neutralize 2 moles of hydrochloric acid. Now, it's asking me for the volume, right? I want the volume of HCl. I'm going to throw it out one more time. It's Monday. It's early in the morning. My students are awake. Who can tell me what I should do next? Where I could go? You know, I just want to see if anybody could figure this one out. The last step. I need one more conversion factor. Yes, yes, good. Excellent. Okay. Violet, Joel, Jonah, Amanda, Aaron, all on the right track, right? Now, if you're the kind of student that needs to stop here in the problem and just work this out and say, you know what, Mr. Dion, I'm going to stop right here, figure out the number of moles of HCl. I've got the number of moles, I've got the molarity, then I can figure out the volume. That is totally acceptable. There's nothing wrong with that at all. I'm just the kind of guy that likes to put everything all in one. I like doing one-stop shopping. So I like to put everything all in the same equation. And so I know that I have a concentration of 0.10 moles of HCl in 1 liter of HCl. And if you're wondering, where did you get that? That's the concentration. It's just 0.10 moles per liter. That's the definition of molarity. And so if you look here, you can see that this cancels out, moles of HCl cancel out, and we're left over with what? We're left over with liters of HCl. Now I've gone ahead and done the math here. You punch all that spinach into your calculator. What did I get? If I can read my own writing, I got 0.034 liters of HCl. You convert that into milliliters in your head. What do I have to multiply this number by to get it to milliliters? What number would I multiply by? Yeah, just multiply by 1,000. Can you multiply this by 1,000? I bet you can. Yeah. You'd move the decimal place over 1, 2, 3 places, so you'd end up with 34 milliliters of HCl. All right, there you go. That's a perfectly reasonable problem. What kind of skills did we use here? Balancing an equation, a little nomenclature practice, some conversion factors, right? There, again, I've said this to you probably 6 times already, but I'm going to say it one more time, that there is no math on this screen that you are looking at right now, that nobody in our class is unable to do this. Every single person who is hearing my voice can do the math. It's a matter of what? Knowing how to set it up. And that is one of the challenging things about chemistry. Well, with that in mind, let's look at the last problem in 4.16 that I want to cover here. This is a titration problem. And I'm not going to reteach the whole concept of titration because we went over this in gory detail last class. I just want to see if I worked it out myself. I know I did, but sometimes my notes can get a little disorganized. Anyhow, I got enough information here. Okay, so this is just your typical run-of-the-mill titration problem. Every ACS final, they always seem to put a titration problem in at the end, and so it's important that you're able to do these kinds of problems. It says here you take a 50 milliliter sample of sulfuric acid and you titrate it with a 0.1524 molar sodium hydroxide. The burette reads 0.055 mils at the beginning and then 33.87 mils at the end. What's the molarity of the sulfuric acid solution? Let me show you a little something here. I don't know if I've taught you this yet, but when you put square brackets around something like this, so if I put square brackets around H2SO4, what that means is the concentration. So this is like saying the concentration of sulfuric acid, and then I'm saying is equal to what? So the whole point of somebody getting out a burette, okay, a couple of my students told me they had done titrations. The whole purpose behind getting out a burette and volumetric glassware and doing all this work is because the scientist or the student here wants to simply determine what's the concentration of my sulfuric acid. I mean, is this so concentrated that it's going to start burning holes through my clothes and give me skin burns or something if I was to come into contact with this? Or is this going to be dilute enough that I don't have to stress nearly as much. Of course, you're still going to be safe in the lab. So let's figure that out. And what's the first thing we have to do? Starts with B, ends with balanced equation, right? We have to make a balanced equation. And so I didn't give myself any room to do that. And so what I will do is I will switch over here to just a blank canvas, and we'll just start, kind of rocking and rolling here. And we'll start by writing out a balanced equation. So I have sodium hydroxide, that's aqueous, and I'm adding it to H2SO4, aqueous. What am I going to form? I'm not going to go over this in gross and dirty detail. I get a salt, which is sodium sulfate, soluble plus water. Now I need to balance this equation. There we go, and there we go. Okay, so now I have a balanced equation. Now, the first thing we want to do is figure out the volume of sodium hydroxide that we're using, because your burette, forgive me for my drawing, okay, maybe I should just give up on drawing. Your burette looks like this. Which I have a bunch of students who are good artists. But anyhow, your burette looks like this, and then you have your stopcock here. You're starting out with a volume, right? You read a burette going down. So the volume at the top is going to be 0 mils. So this should say 0 milliliters, and then it goes down to probably around 50 milliliters. And the thing is that you can read a burette to 2 decimal places. You can read it to the 100th place. And so they're saying you're starting with, what was it, 0.55 mils. That's where you're starting. And then by the time your titration is done, you read the burette again, and it says 33.87 milliliters. So the volume of sodium hydroxide is what is in between these two marks. And so to determine the volume of sodium hydroxide, we're going to take 33.87 milliliters, and we're going to subtract 0.55 milliliters. Punch that spinach into your calculator, and you end up with 33.32 mils, okay? Now, we know the concentration of our sodium hydroxide, right? That has been given to us. They told us that the concentration was 0.1524 molar, or moles per liter. We can also convert this volume into liters, right? Because we know that in 1 liter, we have 1,000 milliliters. I'm getting too excited about solving the problem here, I think. Anyhow, so then that would equal 0.03332 liters of sodium hydroxide. Well, looky. Now we've got the concentration of our sodium hydroxide, and we have the volume of our sodium hydroxide. Can we figure out the number of moles of sodium hydroxide? You bet your bobby socks we can. All right, so let's do that. Let's take and do some dimensional analysis here. We're starting with 0.03332 liters of sodium hydroxide. We know that we have 0.1524 moles of sodium hydroxide in 1 liter of sodium hydroxide. Look, if we were to stop right here, we would cancel out liters of sodium hydroxide, and we'd have the number of moles of sodium hydroxide. But in order to figure out what the concentration of sulfuric acid is, we need to know the number of moles. We already have the volume of our sulfuric acid. They've already told us that we have 50.00 milliliters. All right. So how can somebody guide me and tell me where would I go to get my next conversion factor to figure out the number of moles of H2SO4, of sulfuric acid? Not a trick question. Right, we're going to have to go to the balanced equation. Exactly. Because we know the ratio of sodium hydroxide to sulfuric acid is 2 to 1. So let's plug those numbers in. So we'll put down here, I know that for every 2 moles of sodium hydroxide, I have 1 mole of sulfuric acid. You know what? I am going to stop there for now. And we're going to calculate the number of moles of sulfuric acid. Now, I don't know if I did this. Oh, maybe I did. We end up with, what is it? 5.078 times 10 to the negative 3. No, that's not right. We end up with, that's 2 times as much, isn't it? We end up with 2.539 times 10 to the negative 3 moles of H2SO4. I want you to think about what we've got now. We've got the number of moles of sulfuric acid, and we have the volume of sulfuric acid. Remember that old chestnut I told you last week? I said, well, molarity is equal to the number of moles per unit volume. We have both of these things. This is our N, and this is our V. All we have to do is convert this into liters. And to do that, we just divide by 1,000. So we have 2.539 times 10 to the minus 3 moles divided by 0.05000 liters. I did that in my noggin. I'm just going to double check my math here, make sure it's correct. 2.539 times 10 to the negative 3 divided by 0.05, like that. And I end up with this number, 0.05078 molar sulfuric acid. So that's pretty dilute, okay? Less than a molar. Well, what was the whole point here? And I know I've already said this, but I just want to repeat it. What was the whole point of this exercise, right? It was to take a burette, that's what I've drawn here on the far right, take a burette, take a solution of sodium hydroxide that we know the concentration of, and we knew the volume of it too. We knew both of those things. We knew the volume of our sulfuric acid. All we had to do was figure out the number of moles of sulfuric acid and then use this formula right here. I know that titration problems are not, they're not simple to interpret. The math is not complicated. It's just a matter of setting it up. Give me a thumbs up if you're like, I think I could nail this. I just need a little more time to investigate and to practice. Yeah, it's totally normal for students to take a while to understand titration. So if you're really stuck on the concept of titration, there are several things you could do. You could tackle some more practice problems. Another good option would be, I don't put plugs in for other people's YouTube channels, but you could literally go on YouTube and look up probably Avogadro's number of different videos that just talk about titration and nothing else, and probably go over it very slowly, okay? And the reason why I'm encouraging you to do that, if you struggle with the concept, is because it's such an important concept in general chemistry, and it's even more important when you get to general chemistry too, okay? So I promise you, just like the nomenclature promise I made to you, if you, any time that you spend studying titration and trying to figure it out in your mind, you know, and understanding what the heck is going on in these kinds of problems, it will not be wasted time, okay? I promise you that. It will be a good investment in your time as a chemistry student. Well, let me just go back. Oops, I didn't want to go there. I want to go right here. So this is where we were, and a couple students asked me, you know, where do we end in this chapter? So remember, in the course schedule, I always cover, or I always mention exactly where we stop. So we're stopping at 4.4, and then 4.5, we'll cover that at another time. Anyhow, I just want to point this one slide out. I don't teach this slide. This is something that was, this slide that I actually borrowed from a colleague, so from Dr. Diaz. I share an office with him. This is an alternate way of solving titration problems, okay? It's by using a variation of the M1, V1, M2, V2 problem. But the problem with that equation is that the stoichiometry is not always one-to-one. So you can't just use that. It says here, do not use that. This equation is meant only for dilutions. However, you can put, you know, a reciprocal 1 over the balanced coefficient of your acid and then 1 over the balanced coefficient of your base, and that will work, okay? Again, and you're like, okay, Mr. Dion, you said you don't teach it. What I'm telling you is that it's up to you if you want to try this, okay? Like, it's up to me. Of course, this is a free country. If you are really confident and you feel like this would be beneficial to you, by all means, use it, okay? The reason why I'm not a mega fan of it is because I've taught it, or I've seen it taught before, and I've seen students fall into a trap with it where they'll forget this, you know, and they'll end up, you know, with the wrong answer, okay? So that's just my 2 cents about it. But again, everybody has probably different ways of approaching, you know, the learning process and things. So there we go. So that's covers what we need to know about chapter 4 for now. And I want to get into chapter 14 for a little bit. And again, I kind of want to make this a fun thing. and just kind of go over. I want to distill this, into the simplest possible bits of what you need to know. So some of what I'm going to say will be new, and some of what I'm going to say to you will be things that you already know that will be old hat, and just me rehashing them for you. In fact, I even have some detailed notes. You can't see it, but on my notes that I use as an instructor, I made some notes for myself last semester, and I said, distill this into the simplest possible bits, and then spend time discussing X, Y, and Z. So I'm going to concentrate on the things that I think are most important. And we're going to skip all these different sections here, 14.5 to 14.8. There's a lot of interesting concepts covered in those sections of the chapter in our textbook. If you want to read those, be my guest, but we're going to focus largely on these parts that I don't have crossed out. So 14.1 to 14.4, and then the last two sections. Well, without further ado, let's talk a little bit about the history of elements. And this is more of just an FYI thing. I'm never going to ask you about, when were the elements, when was carbon discovered? When was, neon discovered? No, but just to kind of give you an idea, we spent quite a bit of time in this class talking about the periodic table, but just look at what was known back in ancient times, so ancient times was the one highlighted in gray. They knew about things like copper and iron, silver, gold, mercury, tin, lead, carbon, sulfur. And then later on, people started to, realize, learn about things like platinum, zinc, phosphorus, arsenic, antimony, bismuth, so on and so forth. And anyhow, we could spend all kind of time looking at all of these, but then you can see that, there's some elements that we basically never talk about in this class, like all the ones that are after Lawrencium, have all these newer elements here, some of them, like, some of them, they've only even made a few atoms of these. So Mr. Dion isn't an expert in the synthetic elements. It's not really an area of my interest as far as research goes, but you can see that it took a long time, and you can imagine a lot of people and a lot of ingenuity to discover these elements. But anyhow, when you think about the periodic table and how it's laid out, right? We just look at this beautiful periodic table, or I think it's beautiful, and just a little tiny bit of the history, and I'll never ask you about this, but this is just kind of an FYI, is that scientists, they knew about lots of elements, into the 17 and 1800s, but in the 1700s, they weren't sure exactly how the elements were organized. They thought there must be some kind of organization to them, because they found that when they arranged the elements in order of atomic mass, they found that, that there was kind of a repetition every 8 elements, it says here. And John Newlands proposed what was called the law of octaves. And if you're a musician, that's actually based on the musical notes. Now, nowadays, we kind of look at that and laugh at it and be like, that's silly, based it on music, Well, there is some rationale behind this whole octaves thing, okay? If you studied chemistry before, I'm sure you've heard of an octet. And so you can see that he wasn't totally wild, but that theory, the whole law of octaves, didn't work beyond calcium. So it only got him up to about the first 20 elements. Now, the father of the modern periodic table is Dmitry Mendeleev. And what he did is he took all the elements that he knew, and he made flashcards, or kind of like little cards for each one of them, and wrote down every property that he knew of every element that was known. Okay, so he wrote down the symbol, the mass, the appearance, how it reacted, if it formed oxides, blah blah blah, all these different things. Okay, and then what he would do is he'd lay them out on the table, and he would try to organize them, and he kept organizing them in all kinds of different ways. Now, the first periodic table that he published, that Mendeleev published, didn't look exactly like this one here. It's kind of like it was turned 90 degrees and then flipped over like a pancake. So it was a little bit different. But what's so cool about what Mendeleev did is that he was able to predict elements that hadn't yet been discovered. Now, the most notable example that I can think of off the top of my head is he knew about aluminum, but he was able to predict gallium's, mass, its appearance, its reactivity, density, its, other properties that we haven't learned about yet, like its ionization energy and things like that. He was able to predict that just based off of the periodicity or the repetition. What does period mean? It means something that repeats after a certain amount of time. Okay, there you go. So that's a little bit about the history of the periodic table. Well, let's talk about how our periodic table is divided. Now, the elements that are highlighted in purple here, we call these the representative elements. Anything that has an A over it, so anything that has the letter A over it, so like group 1A and 2A and 3A and all the way up to 8A, we call these the main group elements. Main group elements. And a lot of what we talk about in this class involves main group elements. And then you see that below them, we have what are called the transition metals. Now here they put group 2B in a separate class by itself, but for our class, we'll just say anything that has a B above it, we call those the transition metals. So these are all transition metals here. Okay, and then the last column here, group 8A, those are called the noble gases. Okay, so the noble gases, so we should label that noble gases. What else? Does anybody remember what group 7A is called? Not a trick question.
Halogens.
Yeah, exactly. The halogens. Yeah. So we have the halogens over here. And then in group 1A, we have the alkali metals. And then in group 2A, we have the alkaline earths. And so you're responsible for knowing the names of these groups. So we have the alkali metals, the alkaline earths, the halogens, and the noble gases. Let me also remind you that the vertical columns in the periodic table, so any vertical column, we call that a group. So we call this a group, or sometimes we call it a family. When we have a horizontal row like this, we call this a period. So period, okay? All right, and then the periods, let me just delete that because it's messy. The periods, we have period 1, period 2, period 3, period 4, period 5, period 6, period 7. And then you notice that in here, we have a break here. We call these ones down here, we call these the inner transition metals. So the lanthanides and actinides, we call these the inner transition metals. There are some other like sassy names for some of the groups. Thank you everybody who answered that question. For example, I think I might have told you that copper, silver, and gold, they call these the coinage metals. And there's some other group names that aren't coming to my mind right now. But you have to be aware of the halogens, the noble gases, the alkali metals, the alkaline earths. All right, transition metals, main group elements. You have to know about the inner transitions. You have to know the top row is called the lanthanides, the actinides. So there you go. Now here's something that you probably don't see very often in books is a periodic table where they actually put the inner transition metals into the periodic table. And the reason we leave the inner transition metals down at the bottom is just to make more space. Nothing more than that, okay? So remember, the rows, and I'm just going to rehash a lot of the same concepts here because you really need to know these things. The rows, we call these the periods, okay? And then everything here we call the groups, okay? So the groups, there we go. So group 1, 2, so on and so forth. Now, some other concepts that you need to be aware of are that normally, and there's exceptions to some of the things that I'll say, but normally, elements that are in group 1, like to have a +1 charge. So +1. Elements that are in group 2 like to have a +2 charge, right? And these are things that we've already covered. Elements that are, this is group 13 or group 3A, they like to have a +3 charge. Group 14 or 4A, that's a little bit trickier, but let's go here to group 15. Elements here like to have a -3 charge. Elements in group 16 or 6A, they like to have a -2 charge. The halogens like to have a -1 charge, and the noble gases, they don't like to have any charge. In fact, there are no known compounds of helium and neon, for example. All right, so there we go. So you need to be aware of these groups and their charges. And I explained to you why these elements like to form these charges. And if you don't remember, I'll just tell you quickly that what an element will do is it will lose or gain electrons so that it will have the same number of electrons as the nearest noble gas. Now let's take a look at 2 examples here. If I look at nitrogen, The reason like nitrogen likes to gain 3 electrons and have a 3- charge is because if it gains 1, 2, 3 electrons, it will have 10 electrons. It'll still have 7 protons, but it'll have 10 electrons, and that's the same number of electrons as neon. Now, if you're wondering, what's the significance of all that? That's something that we'll cover in even more detail and later on. And if you studied chemistry before, you've heard of things like the octet rule, and we'll look at that in even more detail later on. But this is just a reminder. Let's look at another example. Aluminum. The reason aluminum likes to have a +3 charge is because if it loses 1, 2, 3 electrons, it'll have the same number of electrons as neon. You can even do the math instead of bouncing your pen around, right? You could just say, well, if I have 13 and I lose 3, then I have 10 electrons. All right, so that is, just rehashing some of the concepts that we know already, especially things that we learned in nomenclature. Again, we have the alkali metals, the alkaline earths, the transition metals, halogens, noble gases, intertransition metals. And these are all things that you need to be aware of moving forward in this class. Now, before we get into some periodic table trends, where did I have it here? Yeah, we're going to talk about periodic table trends for a little bit today. And the student even asked me last lecture, he said, are we going to talk about periodic trends? Yeah, we're going to talk about periodic trends. So it says here that if you look at the periodic table, okay, if we go in this direction here and in this direction down here, basically going from the top right to the bottom left of the periodic table, metallic behavior increases. Metallic behavior simply means the ability of an element to just react. Okay, so the ability of an element to react by losing an electron. Okay, and it says here, since elements are placed in groups based on chemical properties, the periodic table has trends in chemical behavior. So you can imagine that metals that are, in the first group, in group 1A, are probably quite reactive, right? And then if you go over to group 2A, well, since it's going to decrease going in this direction, they're probably a little less reactive, and you would be correct in that assumption, okay? So these are the kind of things that we have to think about when we look at the periodic table. And so we're going to focus right now on 3 concepts, and I'm not going to spend a lot of time on these, but I'm going to spend a little bit of time just kind of going over atomic size, so the actual sizes of the respective sizes of the atoms, what's called ionization energy. Now, ionization energy is the energy that's required to remove 1 mole of electrons from 1 mole of gaseous ions. So if you have any element, even a metal like gold, okay, if you have it in the gaseous phase and you remove an electron from it, okay, how much energy does it take to rip an electron off an atom? That's the definition of what ionization energy is, okay? So removal of an electron in the gaseous phase. And we're also going to look at what's called electron affinity. Now, what does affinity mean? You say you have an affinity for, I don't know, Culver's hamburgers, right? What does that mean? It means you like them, right? So electron affinity is kind of the opposite of ionization energy. It's the energy change associated with the addition of 1 mole of electrons. Now you see that there's some energies associated with that. I'm going to maybe talk more about that as we move on. But before we finish chapter 14, I want you to have some working knowledge of all 3 of these concepts here. And in order for us to really understand that, I'm going to switch gears quite a bit here and talk about a concept that I really wish we were face-to-face for, but I'm going to do my damnedest to try to explain it to you, okay? Now, this is something that I took that's not mentioned in chapter, I don't think it's mentioned in chapter 14, is the concept of effective nuclear charge, okay? But let me tell you right now, that all of these properties that we're going to look at, atomic size, ionization energy, electron affinity, if you did the Learn Smart, electronegativity, all of those concepts can be explained if you understand or based on effective nuclear charge. So let's think about what effective nuclear charge is. Okay, and I'll explain it to you right now. It says, in an atom, starting at the first bullet point, in an atom, there's an electrostatic attraction between the electrons and the protons of the nucleus. Think about it, that makes sense, okay? Because I have the protons in the nucleus, they have a positive charge, that makes sense. Electrons have a negative charge, so yeah, they should be attracted to each other. Okay. Now, in multi-electron atoms. What is a multi-electron atom? That's just a fancy way of saying any atom that has more than one electron. If you're like, come on, Mr. Dion, only hydrogen has one electron. Well, if you have a helium ion, right, a helium cation, that would have one electron. But anything that has more than one electron, I digress. In multi-electron atoms, the electrons do not experience the total attractive force of the nucleus. Let's think about that for a second, okay? What is this bullet point that I have the red mark on? What does it mean, okay? If you have this nucleus, you see we have some protons in here. We have more than one proton. I'm not even going to count them up. The number is not important. But the more electrons, let me back up. If we have one electron, right, just this one electron that I have here, that one electron is going to feel all of the force of those protons, right, pulling it in, right, opposite attract. What if I have a second electron? Are both of those electrons going to feel the same amount of force? No, right? They will not feel the same amount of force because some of the positive charge is going to be pulling on this electron, and then some of the positive charge is going to be pulling on that electron, right? What if I add another electron? Oh, baby, whoa, right? If I keep adding electrons, what does that mean? That means that overall, it says electrons are going to cancel some of the nuclear charge, okay? And we have what are called outer electrons or valence electrons and inner electrons that are called core electrons. And the more core electrons or inner electrons we have, the more they shield the outer electrons or the valence electrons from that positive charge. So the attractive force experienced by an electron in an atom, we refer to that as the effective nuclear charge. Let me explain it to you one more time, okay, in case you're kind of unsure. If I have inner electrons, you see these three electrons that I've drawn in black, they're all right on the edge. Those are outside electrons, okay? Those are outer electrons or valence electrons. If I put a bunch of electrons on the inside, what they're going to do is they're going to shield these electrons that are on the outside. So what effective nuclear charge means is it means like the net nuclear charge that these outer electrons experience. Okay, give me a thumbs up if that makes some sense to you. Okay, it's how much of the nucleus do the outer electrons experience? Kinda? Okay, I'll even take a kinda because, Kenner, as we move on, it should become even more clear. Okay, you can actually calculate nuclear charge. I'm not going to go into that right now. Maybe we'll talk about that in a second, okay? But what I want to explain to you is this. Let's say we have sodium. So sodium is found right here in the periodic table, okay? Sodium is found in the third period. So period 1, 2, 3. Now, how many total electrons does sodium have? Sodium has 11 electrons total. It's element number 11. That means it has 11 protons and 11 electrons. The electrons, so we count electrons like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so 11 electrons. Anything that comes before the period that the element is found in, those are core electrons. So what I mean is this: all of these 10 electrons here, they come before the third period. So those are core electrons. That means that sodium has 10 core electrons, and then it has 1 electron in that third period, so it has 1 valence electron. Okay, so it's got 11 protons in the nucleus, but it has a total of 10 electrons blocking this electron, this last electron from the nucleus. Okay, so what does that mean? Okay, well, it means this: that as we go across a period like this, it says the effective nuclear charge, oops, I meant to go over here first. The effective nuclear charge is going to increase upon moving across a row or a period. Why? Because the nuclear charge is going to increase faster than. You know what? Let me just stop presenting here, and I'm going to talk with my hands, and hopefully that will help. There you go. Okay, I'm really trying. This is a lot easier to explain in person, much, much easier. Okay. Why don't the electrons fall into the nucleus due to their attraction? That's got to do with nuclear chemistry. So we'll talk about that later, but just bear with me right now. So as you go across the periodic table, let me grab my periodic table right here, okay? So as we go across a period like this, what are we doing as we go across a period? We're adding more and more electrons, right? We've got potassium, 19 electrons, or 20, sorry, adding more and more protons, 19 protons, 20 protons, 21 protons, right? So as we go across a period, what's happening to the nucleus? It's getting more and more and more and more and more positive, right? It's getting more and more positive as we go across a period. But what did I say? I said in the period, the electrons that you add, because you're adding an electron and a proton, the core electrons, the number of core electrons stays the same, okay? So all the electrons that come before, the number of core electrons stays the same. So even if you don't follow me entirely, let me just summarize it like this. As you go across the period, the nucleus gets more and more and more positive, but there's no more, the number of electrons shielding the outer electrons doesn't change. Okay, so what does that mean? The net result is this. As you go across a period, it's counterintuitive, right? You think you're adding more electrons, you're adding more protons. Shouldn't the atom get bigger and bigger and bigger? No, the atoms get smaller and smaller and smaller, even though you're adding more matter, because as the protons, or as the nucleus gets more and more charged, it pulls those outer electrons in. It just pulls them in tighter. That's what's happening, and that's what effective nuclear charge is. Does that make some?
Adding more to like the electron cloud then?
You're adding more electrons, but the thing is, you're adding more outer electrons.
Yeah.
Okay. Yeah. The number of core electrons, the number of electrons that are guarding the outer electrons, the valence electrons from the nucleus doesn't change.
So like the max is always 10.
Pardon me?
The max is always 10 then?
The max is always 10. No. No. No, I'm not sure what you're talking about. So anyhow, so it's got, don't worry about numbers right now. All I'm saying is that we get more and more protons. Look at the periodic table. Potassium has 19 protons. Calcium has 20 protons. Scandium has 21 protons. Titanium has 22 protons. As we add a proton, we're adding electrons too, but we're adding outer electrons. The number of core electrons is, for the third period, will always be 18. We're always going to have 18 core electrons, all the electrons that came before it. Okay, so if the nucleus is getting more and bigger and more charged, but the number of core electrons stays the same, it's going to pull those outer electrons in and in and in and in and in, and they get tighter and tighter and tighter. Does that make some sense? A little bit of sense. Okay, good. All right, because effective nuclear charge can really help you understand, what the heck is going on here. All right, so let me get back to sharing my screen. Good. Okay. Now, effective nuclear charge, you're just going to have to kind of take my word for it that it increases going down a column or a group. Okay, that's a little bit more tricky because we haven't really discussed valence electrons, and you don't know what N is yet. It's not number of moles, but we'll talk about that more later. I just want you to get the idea that as the nucleus gets more and more positive, okay, that explains why the atomic radius is going to decrease when we go across a period like this, okay? Let me give you another example, okay? If we start at rubidium here, okay? Rubidium is element number 37. That means that all of the 36 electrons that are going to come before, okay, these are all core, 36 core electrons. So as I go from rubidium to strontium to ytterbium to zirconium to niobium, so on and so forth, the number of core electrons is always going to stay the same, but we're adding more and more electrons, and the protons, we're getting more and more protons too as we move along. So again, the nucleus is getting more and more positively charged, but we have the same number of core electrons guarding that nucleus. And so the electrons are going to be pulled in tighter. Now, again, this is periodic trends. The name wasn't periodic hard and fast rules that there's no exceptions to, because some of you are probably saying, well, Mr. Dion, it looks like, it even looks like the elements get bigger here and then they get smaller again. These are anomalies to the trends. Are there explanations for these? Yes. Do we cover all of these in General Chemistry 1? Absolutely not. We will look at some of them, but the idea is that generally speaking, as you cross a period, the elements are going to get smaller and smaller, okay? Now, the way that, it's kind of laid out in this chapter is to just tell you, and then you're supposed to just accept it. But I like to kind of give my students a little bit of background. Now, the reason why the elements get bigger and bigger as you go down a group, that's probably a little bit more intuitive. It's just because they're getting so much bigger as you go down a group, right? You're not just adding one proton, you're adding like, 10 or, 18 protons, right? You're getting a lot more protons, a lot more matter, bigger what we call electron shells, which we'll learn about in chapter 7. But that is why they get bigger going down a group. All right, so now we've covered atomic size and a little bit about effective nuclear charge. Some people need everything shown in a graph, so of course I had to include a graph here. Here's atomic number, and you can see that the alkali metals, which are group 1A, they're all the biggest elements, right? They're going to be the biggest ones. And does that make sense? Yes, based off of this right here, you can see that they are the biggest ones, right? You can see that the halogens, right, are pretty small. Let's go back here. The noble gases are going to be really small. So you can see them, they're all at the bottom of the curves. Are these perfectly linear curves? No, you can see that there are some exceptions. And in fact, the transition metals don't even change all that much in terms of size. And there's a good reason for that, but I'm just going to leave it as this for now, okay? And we'll get into more detail about it later on. So what's the take-home message is that atomic radius is going to decrease going across a period, and it's going to increase going down a group. And that you should have some bit of idea as to why that happens based off of effective nuclear charge. All right, let's talk about the next one. I always say, as a chemistry teacher, there's 3 absolutes in life. I know you're aware of the 2 of them, which are death and taxes. Okay, but when you're a chemistry teacher, there's 3. It's death, taxes, and electronegativity. Students love electronegativity. For some reason, they just dig it. And electronegativity, we have an electronegativity scale. There are several electronegativity scales. The one that most general chemistry textbooks use is what's called the Linus Pauling scale, or the Pauling scale, which was developed by Linus Pauling. And he assigned fluorine, which is the most electronegative element, he assigned it a value of 4.0, and then he based everything else off of that. But electronegativity, and you're like, well, it says here, is the ability of a bonded atom to attract shared electrons. So it's the ability of a bonded atom to pull electrons towards itself. All right, so fluorine has the greatest ability to pull electrons towards itself. You can see here cesium and francium have the least, or the lowest ability to pull electrons towards themselves. Now you got to remember that electronegativity and electron affinity are 2 different things, okay? Because earlier I told you that electron affinity was the measure of how much an atom wanted to take on an electron. Anyhow, but electronegativity, it's in a bond, okay? A bonded atom. And I put a little blank page over here because I wanted to share something with you, okay? If we think about the water, not the water molecule, the water molecule, okay? You've probably seen it drawn like this before, right? H2O, like this, where it has this bent shape, okay? Where it has this kind of angle between the hydrogens. We're going to learn about that later in the class. But I want to address something that I did talk to you about earlier on. I told you that water was a polar molecule, was what we call polar. So water is a polar molecule. And I'm going to introduce you or explain you to why that is. If you look at the periodic table, you can see that oxygen is in fact the second most electronegative element in the periodic table. It has a value of 3.5. So oxygen is 3.5. And if you look at hydrogen, it's kind of put in a funny spot over here, and I'll explain why later. But hydrogen has an electronegativity of 2.1. So what that means is in these 2 bonds right here, the oxygen and the hydrogen are sharing the electrons, right? That's a covalent bond, but is it equal sharing? And the answer is no. It's just like my daughter is 5. Her and I like to go to Costco sometimes, and we'll share a slice of pizza. Is it equal sharing? No. Dad probably gets more of the pizza slice than my little girl, right? So it's a sharing, but it's an unequal sharing. And the way that we represent that, there's a couple of ways that we can do that. But one of the best ways we can do that is we draw an arrow going towards the direction of the element that is more electronegative, and then we put a cross down here. So these represent polar bonds. So polar bonds. Another way of representing that oxygen is more electronegative than hydrogen is to put these little delta signs here. So delta minus, because oxygen is more negative, it's It's not an anion, it's just got more of the electron density. And that's going to leave the hydrogens kind of left out like that. Okay? Give me a thumbs up if you follow me on electronegativity a little bit. All right, thanks, Matthew. Perfect. So what you need to know right now is that electronegativity is highest in the top right corner and lowest in the bottom left corner of the periodic table. Okay, so that's another concept. Is it already 10:20? Shoot. I was thinking we'd have more time to talk about all these things. So I'll kind of go over these things quickly. Ionization energy, I went over this already, is the amount of energy that it takes to remove an electron from the gaseous atom in the ground state. So this is a definition I already covered. I want to go over this concept with you, though, how ionization energy. Imagine you have an element, okay, in the gas phase that I just have highlighted. Okay, imagine you rip an electron off of that. Well, of course, it's going to take energy to do that because there's a positively charged nucleus that's attracting that negative electron. Okay, you're like, Mr. Dion, I already know that when you remove an electron, you're going to form a cation. Okay, cool. What's going to happen? I'm going to throw this out there to my students. You see this cation that I have highlighted in green? It says a gaseous cation, and it says second ionization energy. Do you think it's going to take more or less energy to pull a second electron off of this element? So you take the first one, you make a cation. Do you think the energy for the second ionization energy would be higher or lower? Would it take more or less energy? Violet says more. Yeah. So the mores have it. Let's think about it. Why would it be more? The nucleus didn't change. It still has the same old dang positive charge, but now you've got less electrons. So those electrons are going to be held even tighter. Now the atom's like, don't take my electrons. Don't take any more of my electrons. So you pull a second one away, it takes even more energy. So now you can imagine that if you were to pull off a third electron, then it takes even more energy, right? It says it right here. It's summarized that the ionization energies keep increasing. Are you okay? Blake, I'm not sure what that means, but anyhow, so if you look at the first 20 elements, okay, you can see that, let's just pick any element at random. We'll just pick a random element, okay? We'll pick aluminum. I don't know why, but let's just choose it. You can see that you pick the first electron, takes 578, this is kilojoules per mole. The next one takes, triple the amount. The next one, right? And then all of a sudden it makes this huge jump, okay? More and more and more, okay? Anyhow, I could talk to you about this jump here, like the big increase in ionization energy, but anyhow, I kind of got the point across and we're running out of time, so I'll keep moving on. What else? Let's just talk about hydrogen for a second. Hydrogen's such a cool element. It's not my favorite element. I'm an organic chemist. I'm more of a carbon guy. But hydrogen is, it's the first element. It's the most abundant element in the universe. In the entire universe, hydrogen is first, okay? Helium is second. Anyhow, hydrogen is really simple. It's got one proton, one electron, okay? What else? Hydrogen is a diatomic molecule. Okay, we've learned about the diatomic molecules. It's colorless, odorless, very low melting and boiling point. Does anybody know what this is here? The Hindenburg. How do you spell Berg? Is it B-U-R-G? I don't know. Anyhow, the Hindenburg, which blew up in Lakehurst, New Jersey in the 30s. You could Google that if you want and watch the YouTube video of it. Does anybody know the famous expression about when it's blowing up, what the guy says, the famous expression? That's right. Gunnar says, oh, the humanity. You know what, Gunnar? When you're a chemistry teacher, you look at, you say that all the time about everything. Anyhow, hydrogen is most abundant in combination with oxygen. So most of hydrogen on the Earth is obviously found in water. But I wanted to share a couple more things about hydrogen. Okay. Where does hydrogen belong? If you look in some, maybe a high school chemistry class or something, you might see a periodic table that will have hydrogen obviously as the first element. Has anybody ever seen a periodic table that has hydrogen shown in two places, shown it above the halogens as well? Anyone? Yeah, so it's somebody says yes, somebody says no. Okay, to tell you what, Violet, it's not that uncommon. I've never seen a periodic table that had hydrogen in group 4A, never in my life. But it's not that uncommon to see hydrogen put here, to put it in two different places. And there's a reason why. It's because hydrogen only has one valence electron, but so hydrogen, what does hydrogen have in common with the halogens? Is that if it gains one electron, so if hydrogen gains one electron, it'll have the same number of electrons as a noble gas. Okay, so if you think about fluorine, right? Fluorine only has to gain one electron, and it has the same number of electrons as neon. So that's why hydrogen does have some commonalities with neon. Now, this why you would put it in group 4A is actually pretty interesting. It's got quite a bit of similar reactivity to the elements that are in group 4A, carbon, silicon, germanium, tin, lead. But I would say an even easier way to think about why you would put it in group 4A is because it's got half the number of electrons as a noble gas. So helium has 2. So when you're over here, elements like carbon, they have 4 electrons, 4 valence electrons, so it has half the number of neon. Anyhow, I'm not going to ask you about that anyway, so don't stress about that. More of an FYI thing. What else? Other things that I wanted to clear up with you guys, just to make sure you're all on the same page. I know something else I wanted to tell you is, do you guys all know the difference between, did I teach you the difference between hydrogen, a hydrogen ion that's a cation, a hydrogen with a minus charge, and H2? Does everybody know the difference between all 4 of these? Because they will come up in my speech, in my everyday parlance. All I see is that Dayona put NERP. I'm not even sure what that means, Dayona. But just to be sure that we're all on the same page. Okay, some people are saying no. Okay, so let's go over these. So when you have just the letter H, that means the element hydrogen. So that would be if you're just talking about element, hydrogen by itself, on the periodic table, element 1. Whereas a hydrogen cation, so when hydrogen loses a proton, we get a hydrogen cation. We call that a proton. Okay, so you could call it a hydrogen ion, but I can tell you right now, if you're talking to another chemist and you said, "What about that hydrogen ion?" They wouldn't laugh at you, but they'd be like, "What? What are you talking about?" More commonly, we say a proton. And if you're like, "Well, why do you call it a proton?" Well, think about a hydrogen atom. It's just got one proton and one electron. If you lose the electron, what have you got left over? You've got a positively charged proton. And so that's why we call H plus a proton. H minus, does anybody know the name of H minus? So for H minus, it has to have 2 electrons. Does anybody remember what that was called? I would have covered it in my nomenclature. Anyhow, in case you don't remember, when hydrogen has a negative charge, that's called hydride. Hydride. Okay, so hydride. An example is if you had this compound, so say if you had NaH, that's an ionic compound, and it's called sodium hydride. And then H2, that's hydrogen as well. So that's hydrogen. Maybe I should be consistent here. Let me write it down. I'll put molecular hydrogen. So this is molecular hydrogen. Okay, and this is the hydrogen that's a gas that blew up in the Hindenburg. Okay, does that clear these things up a little bit? Because they come up pretty often in chemistry. So I want to make sure that you all are on the same page. Good. Thanks, Matthew. Thanks, Violet. Good. Okay. Let's see here. I already covered this. So these are hydrides here. Metallic hydrides, I'd never ask you about that, not in this lifetime. So I just want to skip down here to something that I think is really important. There's not enough time for me to go over all these things. But let's cover, just for fun, did you guys know that the alkali metals, did I tell you that you can cut an alkali metal with a knife? Like sodium, you can cut it with a plastic knife. It's very easy to do. In fact, I've done it a number of times in my life. And there's a good reason for that. And I'm not going to go into the details about why it's so soft. It's covered in the textbook. But I think I might have told you that some guys when I was in graduate school took chunks of sodium and they were lighting a cigarette with an ice cube. So I wouldn't try that. But anyhow, let's take a look at this because we talked about the size of elements, right? We talked about atomic radius today. If you're like atomic radius, all I meant was the size of an atom, okay? Let's talk about lattice energies. The lattice energy is the energy associated with an ionic compound, like how strong an ionic compound is, how strong the cation and the anion are held together. I just want to cover one quick concept here with you that I think is kind of a fun one. If you compare these chlorides, lithium chloride and beryllium chloride, these lattice energies here are reported in kilojoules per mole. And you can see that beryllium chloride is much stronger than lithium chloride. Why would that be? Because lattice energy, says here lattice energy, the electrostatic force, is based off of Coulomb's law, which is the lattice energy is equal to Coulomb's constant multiplied by the charge of the two ions divided by the radius squared. Okay, let's think about that. What happens when I go from lithium to beryllium? I go from a 1 plus charge to a 2 plus charge. That means I'm going to increase the magnitude of Q, even though chloride doesn't change. And what else? How would I compare the size of a lithium to a beryllium? I'll just ask my students, what's smaller, a lithium or a beryllium atom? Which one's smaller? Yeah, exactly. Beryllium is smaller. So that means it's going to have a smaller radius. And what's that going to do? It's going to cause the lattice energy to increase. So that explains why as we go from lithium chloride to beryllium chloride or from sodium chloride to magnesium chloride, that explains why the lattice energy gets stronger and stronger and stronger. I'm going to skip all this here. I'm not going to cover all this here. And maybe we could skip all that for now. We've covered all this stuff. You know what? We've got 9 minutes left. And I'll just mention the noble gases maybe quickly. The whole part about oxidizing and reducing, I haven't covered that yet in class, so don't worry about any questions about oxidation and reduction until I cover that in full detail. Noble gases. And so the way I wanted to end this lecture is this. I know I kind of jumped around in the past, hour or whatever with you. We've looked at quite a few things, but I think we should end here. And these are questions that come from your next practice midterm. Okay, these are the kind of questions that I would expect you to answer based off of what we covered today. Now, you might look at these questions and say, Mr. Dion, these aren't exactly what you covered today. No, not exactly, but I just wanted to spend a day and just kind of give my students a little bit more of a tour around the periodic table and talk about the sizes of atoms before we really dig in chapter 7 and start looking at quantum theory. So let's take a look at a few practice problems here. It says lithium metal. So lithium is a metal. It says lithium metal reacts with water to form lithium hydroxide as one of the products. Okay. Then it says calcium metal. I'll write it down here. Calcium is also a solid. Reacts with water to form calcium hydroxide, and they even gave us the formula. What is the most likely product of the reaction between barium and water? Could anybody just tell me what would you probably get when you react barium solid plus water? And it's not a trick question. And you can answer the question. Yeah, exactly. Violet put BaOH2, right? She put BaOH2, which is the formula for barium hydroxide. Okay, and so the answer is right here. Now, if you're stuck and you're like, I'm not sure where she got that answer, the whole rationale behind this question is nothing more than this, is that you understand that lithium comes from group 1A. And so it likes to have a +1 charge, right? +1. Hydroxide is always -1. And so we have a +1 and a -1. Calcium is from group 2A. And so it likes to have a +2 charge. And so we have +2 and we have -1 times 2, which gives you -2, right? And they are going to cancel each other out. The only thing that you have to be able to extract from this question is that calcium and barium come from the same group. They're both from group 2A. And so barium should have a charge of +2, and so it should combine with 2 hydroxides. That's all you need to get out of this question. Give me a thumbs up if you follow me on that. Cha, all right, perfect. All my students still paying attention. All right, great. Wunderbar, perfect. Nothing more than that. Nothing more than that. Let's take a look at this one here. This question is in the exact same vein. It says, given that sodium chloride and magnesium chloride have these formulas, what do you think the formula would be if you made a compound made of boron and bromine? Not a trick question. Who could just give me an idea? I'm not even going to walk you through the answer yet. I want to know if my students can figure this out. Okay, I get some answers here. I got a few different answers. All right. So look, bromide is never going to change, right? Bromide is always Br -1. What group is boron in? Can anybody tell me that? We'll boil it down here. Group what? Boron is in group 3A. 3A, okay? So boron is in group 3A, exactly, yes. So based off of that, what kind of charge does a boron ion like to have? Yes, exactly, +3, right? So it's going to want to have a charge of +3. So if I've got -1 and +3, how many bromides do I need to balance out my bromine? My boron. If the boron is +3, then I need bromine, and I'm going to need 3 of those, right? -1 times 3 gives you -3. So the formula must be BBr3, or boron tribromide. Give me a thumbs up if you follow me on that one. We've got 3 minutes left. I'll maybe turn it into 25 minutes, but anyway, I'm kidding. All right. You guys probably have a long ways to go to get to your next class. Are you feeling confident about these questions? I hope so. Let's try one more. Let's see here. Let's try this one. It says titanium. Ooh, titanium's transition metal. You can do all kinds of cool stuff. You can make titanium 4 chloride, titanium 3 chloride, titanium 2 chloride. Which of the following formulas represents a compound that you would expect titanium to form with fluorine? So these, and what compound would you get from titanium and fluorine? Oh, sorry. Which one would you not expect? Mr. Dion needs to wake up. Not expect. I'm just going to throw that out there to my students. I see Violet and Sierra have the right answer. Yes, Deona. Yes, TIF5. So that I shouldn't cross it out. That's the answer, isn't it? Right, because both chlorine and fluorine are halogens. Okay, so that means both are going to have a charge of -1, chloride or fluoride. So that means that fluorine is going to be able to make all the analogous compounds. You're going to have TiF4, you're going to have TiF3, and you're going to have TiF2. F4, F2, F3. You're not going to have TiF5. Not going to do it. All right? Okay. Let's see here. Stop. Boop, 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 boop.